It's a wonderful place to be here, and thanks, Freddie, to make such a wonderful arrangement. I'm really looking forward to the coming days, particularly the dinner. I think it's a really nice place for the dinner at this tower. I'm Shu Tingyang. I'm working at the Danish Meteorological Institute. I'm the coordinator of the TipESM project. The project is, as you see from the title, it's exploring the tipping points and their impacts using Earth system models. And we are now about a little bit more than a year into the project. And so we have already got many exciting results and simulations. And I will try to use not much time because I think we have a very exciting program in the coming 2 days, and also in the following days where we have our own back-to-back project meetings. And so you will hear much more on the things I will present here, and in more details. So for those who are not familiar with the project TipESM, we have, as you see from the title, the project objectives, or the overarching objective is to deliver a step change in our understanding of the climate tipping points in the Earth system. And of course, together using the Earth system model, we will do a series of research, including understanding the impacts of the tipping points to the ecosystems and society, and combine with to understand, try to deliver the early warning indicators and safe emission pathways that can minimize the impact of the tipping points. So the key is the Earth system model. The key tool in our project is the Earth system model. Why Earth system model? I think you don't need me to do a lot of introduction, but as you know, Earth system model can represent explicitly the physics and biophysics of the tipping processes. And it can include the physics and the interaction, the feedbacks between different tipping points. So it allows us to do not only see what happened, but also to understand the mechanism and the physics behind it. And as an example, here it's an example of the Earth system model, UKESM, where you can see the model include, besides the normal AOGCM, where the atmosphere, ocean, sea ice couple together, it also includes the atmosphere, chemistry and aerosols, the marine biogeochemistry, and also the land physics and the dynamical vegetation included in the model system. So we are able to say, simulate explicitly. In addition, I forgot to mention that in this UKESM, it also have an interactive dynamic ice sheet model that's representing the ice sheet of Greenland and the Antarctica. So as you see here, the model can simulate the dynamic interaction of Greenland ice sheet and Antarctica is not shown here, but the dynamic and the leading to the change of Greenland ice sheet due to climate change, and also the feedback of the ice sheet processes back into the climate system, in particular the ocean circulation like AMOC. And as you see here on the left, the model can have a rather realistic representation of the missing layer depths in the North Atlantic subpolar gyre regions. And it also simulates the missed layer depths collapse in the future. So it actually can represent or simulate the tipping phenomena. And in the project, in the past year, we have an extensive collaboration together with the TipMIP, the Tipping Point Modeling Intercomparison Project, and many of the Earth system model groups internationally, and to discuss, to build the experiment protocol for Earth system models that can force us to investigation of the tipping points and tipping point interactions. And the experiment protocol, we decided that should be an emission-driven, run in an emission-driven mode, start from the pre-industrial control, where as our reference, and then start from branch from the pre-industrial, we have a ramp-up simulation to force the climate have an warming, keep in a global warming rate at about 2 degrees per century, and then at some levels of the global warming, and we stabilize the simulation by putting setting a zero emission in the model, and so we can use those simulations to investigate the likelihood of the tipping dynamics and how they interact and the impact. And then to investigate the reversibility of those phenomena, we also run and ramp down simulation. And so to look at if we have the system able to go to the forcing are reduced and how does the tipping phenomena will change or not. And currently, there are already 13 Earth system modeling group had committed to perform those experiments. Among those, 6 of the European groups that joining the project TipESM had already performed, have finished, complete those experiments, or are ongoing of making those simulations. And there also the CESM American group also had performed those experiments. The Japanese MIROC modeling group also had performed the simulation, and as well as the Australian modeling group assess. As example, here shows the surface air temperature response to those protocol, and also some of the models we actually also try to see at the more than the tier 1 ESM simulation protocol, that we have more warming levels in the simulation. And the protocol is based on the assumption that the response is calculated based on the transient climate response to the CO2 emission, accumulated the CO2 emissions, and also at the zero emission rates, that would lead to a warming stabilization. And as you see here, most of the model, the simulation seems to be able to hold this assumption. And even though, particularly at the low warming rate, low warming levels. And for some models, when the global warming levels are strong or high, they seems to, the warming seems to continue. And that's actually indicating the feedback mechanism between the climate and the carbon cycle. And to check the AMOC, how the AMOC will respond in these simulations, as you see here, we've given some example of different models in the project. As you see, during the ramp-up run, the AMOC will decline constantly, but it seems no abrupt change or abrupt collapse will happen, even though the AMOC strength will continue to decline. And at the zero emission, however, the response seems to be different from model to model and from different global warming levels. And as you see here, at the lower global warming levels, some models have a recovery of the AMOC, and some seems to stabilize the AMOC at the relatively low level. And but on the very high global warming levels, these AMOC will continue to decline, even though probably at some sort of a less strong as the ramp down run. And then on the recovery simulation, when we have the rundown simulation, the AMOC seems to recover and recover faster than the rundown. As you have here, some of the model had a dynamical ice sheet model included. I don't think I have time to talk any details, but you will hear after the break, where from 2 presentations where it will present some earlier results on how to identify if we identify any tippings in the ice sheet and how they change and also this kind of simulation will enable us to continue the study on investigating how the interaction of the ice sheet melt and the ocean, particularly the AMOC simulation. And one of the goals of this project is, of course, not just making simulations, but to understand what the tipping point. Can we identify any tipping points in both the physical system and also the biogeochemistry system? As you see here, in the project, we have developed an automatic cataloging method to apply this method on the simulations and try to identify in the physical space if are there any tipping points. And as you can see, there are actually in the current Sim6 example, we could identify both the abrupt change indicating by the small letters and those dots, big circles, and also complete the state change of the phenomena, and like the sea ice, where the largest red circle, where you see the sea ice will be completely gone in the future, and also you see like AMOC, there are also some the change of states that are identified. And currently, this method has been also tested and adjusted to the ocean biogeochemistry variables, and particularly you see here for the net primary productions, where the sort of abrupt change are also identified in some of the model simulations. We also tested the early warning indicators for the Earth system model simulations. Here is just a very early test results where we applied the classical early warning indicator method based on the critical slowdown theory and check if the model are able to simulate abrupt change like sea surface salinity in the North Polar drier region, and see, as you see here, we are able to identify some of the features that indeed there are critical collapse of the subpolar gyre, but the method seems to be sensitive to the choice of like the amplitude of change and the duration where we calculate those indices, and the more research will need to be carried out during the project, and particularly we will apply this research on the simulations we made in the project. And the project also have a large element on identifying climate-driven tipping points in the ecosystem and the society. In the project, there are many, here we listed 9 subsystems that could be tipped in the future, and group it into 3 big realms of territory ecosystem, marine ecosystem, and the societal system. And we applied both the data from our simulations and developed either the Earth system model or special ecosystem models to understand how those elements are changed. And here is an example, a model and a process-based model for great ape population dynamics are developed, and that are driven by climate information and encoding in many different processes and combined with the data had already published, and to understand how the ape population will be changed, and if it could tip in the future. And another area is to assess the impact of the tipping points. And as you see, and there are some early results now already showing that when the subpolar gyre will collapse, and it seems that there are some area in Europe might increase of the heat, warmest days under the heat wave in connection with the tipping of subpolar gyres. And to summarize, as we said, we have developed the protocol, and the simulation are already ongoing for the study of investigation of the tipping points in the Earth system. The data will be available soon on the ESGF data nodes, and there are many research going on at the moment to study both how to identify the tipping, if we could predict the tipping, and also how the tipping elements are interact with each other. But we do not only the, so to say, the TipMIP simulation, or in the project it is the TipESM core simulation. There are also some other simulations we think we need to carry out to be able to fully understand the tipping phenomena. And one is the tip core experiment, tip force experiment, we call it, that so to say, to make it happen, if we don't see a tipping, and can we make it happen to make the tipping happen in the Earth system? And the protocol had already been discussed, and the simulation will start soon. And there are two other simulations that the project will carry out. One is the TipESM ensemble simulation, where we will, if we find any tipping phenomena in the above two simulations, we will then try to understand, to identify the generate an ensemble of events, and to study the downstream consequence of the impacts, and also the tip domain experiment, where we use the offline models to understand the robustness of the tipping points. I will stop here, and I'm sure there will be many more results you will hear in the coming days, and we are really looking forward to simulations. Thank you. That was good.